I'm Mike Ringenburg from Cray. I'm giving a talk that's normally given by my colleague Pete Mendergirl here, but he and his wife recently had a child, and so he didn't want to, for obvious reasons, wasn't thrilled to travel, so I said I'd come here and give this for him. I've seen him give this talk many times. I probably know most of it by heart, so don't worry. But if you have any real hard questions, I put his email up there as well, just in case. So what I'm going to be talking about today, standard legal disclaimer we always include, what I'm going to be talking about today is both the motivation for scaling up deep learning training and some of the things we found and some of the learnings that we've had as we've looked at this problem at Cray and with some of our users and partners. So, as we know, a trained neural network is a powerful tool for a number of problems, for pattern recognition, classification, clustering, prediction, things of that sort. And scaling of deep learning allows you to tackle problems that previously you might not have been able to attack. Models that take a very long time to train. You can shrink the training time from weeks. We've seen cases where we've shrunk training time from weeks down to minutes or hours. We can also significantly increase the frequency at which models can be retrained with new or improved data, which in some use cases can be very valuable. So in this talk, I'll be reviewing some of the techniques and some of the tips and tricks that we've learned as far as scaling up deep learning and how do you actually scale up deep learning successfully and still get good time to accuracy and still get good convergence, because as maybe some of you might have tried this, you might have seen some of the issues you run into as you scale up to very large batch sizes and start seeing more difficulties with getting the learning rate just right and adjusting the learning rate and what optimizers you use and things along those lines. So I've included a few tips. I've also included within the slide deck, there's kind of a handy list of references of some of the best papers that we found about this that can sort of help guide your exploration further. So I'm going to start with a very quick overview of what deep learning is all about, just to bring everybody up kind of onto the same page. For some of you, this may be a review. If any of you were at the Big Data Center Summit at the NERSC lab about a month ago, you've actually probably seen these slides. So if you were there, I'll excuse you if you want to check your email over the next few slides. I was also going to cover how to run TensorFlow on Theta, but I believe that's been covered already today, so I won't waste time on that. So I'll jump right into, after I go through my brief overview of deep learning, I'll jump into some of the methods that you can use for parallelizing TensorFlow, both the built-in methods, gRPC, as well as some of the newer MPI-based methods. So there's the Horovod framework developed by Uber, and also the Cray machine learning plugin that we've developed. And I'll talk a little bit about some of the motivation there and why both we and Uber chose to use MPI as opposed to the gRPC-based model that Google uses in TensorFlow. And then I'll talk about some of the tips and tricks we've learned about actually achieving good convergence at scale. And I'll give a brief example of how to use the Cray PE plugin. And it actually, the example there will actually point to some files that are available on Theta. I'll have some instructions for you on how to run that and try that out and look at how the training script was changed to take advantage of the Cray plugin. So first, just a brief foray into sort of giving everybody a brief introduction. I like to call this talk De-mystifying Deep Learning. It's kind of something that's evolved over time, contributed to by many people at Cray as we've gone around and talked both within Cray and to some of our users about what deep learning is all about. So I want to give credit to Pete, like I mentioned earlier, also to Jeff Dawson at Cray, who contributed a lot of the slides in this section as well. So I think the best way to explain deep learning is with an example. So imagine you're an organic gardener, and you want to deal with pests, insects in your garden that are affecting your vegetables. But as an organic gardener, you don't want to use a pesticide. So you want to build a robot. And you want this robot to be able to recognize 10 different types of common insects found in your garden and decide which ones it wants to kill with its little laser. So we're talking about building robots with lasers. Is always fun. So our robot's going to have a camera. It's going to capture images, let's say JPEG files of the insects that it sees. And now the robot needs some program to classify each of these JPEGs according to which of the 10 types of insects was photographed. So our idea here is we have our program here that's supposed to take some JPEG image and decide, is that a Japanese beetle? And if so, I should probably zap it. So, as I said, our input here is a JPEG. I believe that is a Japanese beetle, although I'm not an entomologist. And our output then is going to be a classification of this image into one of these 10 categories for the sake of this simple example here. So if you imagine trying to do that with sort of a standard, declarative C program, I couldn't even imagine how you do it, how many if statements would be involved in trying to look at a bunch of pixel values and figure out what type of insect it is. So this is sort of a classic AI, artificial intelligence problem. If you can't easily get to the output from the input with a bunch of loops and conditionals, we call this an AI problem. So if that doesn't work, how can we do it? So the basic idea is what we're trying to do is we're trying to create a mapping here from some set of inputs to some set of outputs. This is, of course, a function. And any function can be approximated using a good sort of approximation function with a good optimization technique. So how can we determine a good approximating function? Well, you want to choose its form, and then what you want to do is minimize the overall error at some set of known inputs with some set of known outputs. Essentially, you're just doing curve fitting here. So in order to solve this problem, we just need to find the values of the free parameters of our approximating function that minimize the error, and doesn't matter how we do it. So this is essentially what training a machine learning model is all about. One common method used for training is called gradient descent, where you have some set of known inputs, like I said, and you calculate the error for each of those known inputs and outputs, and then you calculate the gradient of the error. So that's sort of the direction in which the error most steeply increases. Then you take a step in the opposite direction, the direction of the negative gradient, and you check if you've achieved good accuracy. If not, you repeat the process. So you're just sort of stepping through the error space here, looking at the error at each point, looking at the gradient of the error to figure out which direction to step in order to reduce your error. So one really useful kind of approximating function that has been used, that is what's used in deep learning, is a deep neural network. So the basic idea here is we have these neurons, we have these, which are essentially nodes, you can think of them like nodes, connected by these weights here that map the output from each of these into the input of the next layer. And it turns out that these deep neural networks have been found to be very good approximating functions, which can approximate any continuous function arbitrarily well with enough training. So why are we interested in this notion of deep neural networks and deep learning training as a high-performance computing company? Well, deep learning training is a classic high-performance computing problem. There's a large compute capacity required in terms of flops as you're doing your forward propagation through this neural network and your back propagation through the neural network. If you are distributing this training across multiple nodes, there is a large communication component, so fast interconnect is useful. And one thing that we've started to really see more and more as we've taken some of these networks, some of these models, and scaled them up to very large degrees, very large numbers of nodes, is that the I/O can become a significant bottleneck. So a good storage system, fast parallel file system can be very helpful. There's actually at least a few papers coming up at SC18 that involve scaling up to thousands of nodes, and one of the ones that I was involved in, and one of the ones that I was chatting to another researcher about, we both ran into very similar problems and came up with sort of our own unique solutions to that. But this is actually an area that's kind of an active area of research and development here, trying to figure out a more generalizable solution to handle the parallel I/O needs of deep learning training, which is slightly different from your standard HPC problem, where your standard HPC problem, you do you basically do a lot of writes. You very rarely read. In a deep learning training, you're reading a bunch of data many, many times. So why do we want to scale out deep learning? Well, some of these models can take, as I mentioned earlier, many hours, days, even weeks to train if you do it on a single node. But there are techniques that allow you to strong scale that training and strong scale the time to accuracy, provided that you're able to figure out how to achieve convergence with the larger batch sizes. And I'll talk about that a little bit later in the talk here. Another way that sometimes people like to scale their deep learning training is they use the scale of the machine for hyperparameter optimization. So there's many cases where you don't know what your correct learning rates, momentums, number of layers, size of layers are. And so you want to try a whole bunch of things. There are various methods. There's genetic algorithms. There's Bayesian algorithms. There's grid search algorithms for exploring the space of hyperparameters. And you can also take advantage of the scale of a large high-performance computing machine to try out and more effectively search the space of hyperparameters. So these are kind of the two methods. There's the pure sort of scaling of an individual training one, and then there's doing more of an ensemble approach where you're trying a bunch of different. What I'm going to focus mostly on in this talk here is scaling up a single training run. That's where I think some of the more interesting issues come in. But I'm also happy to talk if anybody wants to talk after about hyperparameter tuning. This is an area that is a lot of interest to us, and we've been doing some work in this area as well. But this talk, I'm going to be focused mostly on the scaling and training, that aspect of it. So there's two basic techniques for scaling up the training of your deep neural network models: data parallelism and model parallelism. And these really are exactly what they sound like. So in a data parallel training, you are looking at some set of samples in each step of the training. We call this a mini batch. And in data parallel training, you take your global mini batch and you break it up into a number of local mini batches that it's looked at, by each process. And then there's kind of two ways you can then approach it. Once each of the local processes finishes evaluating its local mini batch, calculating its gradient, you can have everybody sync up and average all of their gradients together, and then start up onto the next step. So this is a synchronous data parallel stochastic gradient descent. The other approach that's sometimes used is asynchronous training. So here, your processes are providing their gradients, sending it out maybe to a parameter server that's getting updated regularly as it receives new data from new processes that complete their local mini batch. But you're not waiting. You're not doing any synchronization here. So this, of course, lets the processes be more efficient. But the problem here that sometimes arises is you can run into some more difficult convergence issues in these cases because the models may drift apart. So with a synchronous data parallel model, your models start the same. They're always averaging everybody else's gradients together with theirs. They're proceeding in lockstep, and so the models don't drift between nodes. Whereas with an asynchronous data parallel stochastic gradient descent, you can actually end up with the model starting to drift. And so the gradient that's computed from one particular version of the model on node 1 may be different than what it would have been if it had been looking at node 2. So when node 2 updates based on the gradient, it's updating based on the gradient computed with a different version of the model that's drifted a bit. So there are some techniques that can be used to help resolve this. But in general, we found that it's much easier to get good accuracy and convergence with the synchronous approach. So we focus mostly on that with some minor tweaks, and I'll mention those as we go through here. The other approach is model parallelism. So in model parallelism, you have a single model where you're decomposing the layers of your model, the layers of this deep neural network across different processes. So instead of parallelizing across the data, you're parallelizing across the layers of the model. There's also possible hybrids have been proposed and used by some folks where maybe you'll do model parallelism across a small number of nodes and then data parallelism across these sort of parallelized models. In this talk, I'm going to be focusing on the technique that's used by both the Horovod framework and by the Cray plugin, which is synchronous data parallel stochastic gradient descent. So the basic algorithm here is outlined in this pseudocode right here. So basically, you're going through a number of steps. You can think of these are basically the mini batches I was talking about. Each process will have its local mini batch, its local set of samples that it's looking at during the current step. It will compute gradients there. It will do an all reduce to combine all of the gradients with all the other nodes. Divide by the number of ranks. So we're basically taking an average of the gradients computed by every node. And then once it's done that all reduce and gotten that average gradient from all the different ranks, then it will apply the gradients locally. So really where all the action is happening here is this compute gradients, very compute intensive, and then this all reduce that can be very communication. What's not shown, of course, as I alluded to earlier, is the I/O activity and possible augmentation of data, which happens sometimes. Those we don't get into in this talk, but I'm happy to chat later about that if people have questions about I/O. So TensorFlow does have a built-in method for doing synchronous stochastic gradient descent called gRPC. The problem with gRPC, it doesn't scale that great beyond relatively small tens of nodes. It's also can be somewhat difficult to use. The user has to specify a lot of information and do a lot of tuning as far as how many parameter servers to use, etc. And I'll show some of the impacts of that in a couple slides here. But first, I want to give a little diagram of how this works. So the gRPC approach is parameter server based, which means that each of the devices, the GPUs, the Xeon Phis, whatever it is locally computing its gradient, sending it back to this server, which is responsible for doing all the combinations and averaging and sends them back out. There's also asynchronous versions of that as well. But as you can imagine in this model, one of the hard questions might be deciding exactly how many of these parameter servers you need and how many worker devices for a given number of worker devices. And it can be very sensitive to that, as we show here on this graph here. So here on the right, what this is showing is on the x-axis here, the number of parameter servers. On the y-axis, we have parallel efficiency. And each of these lines represents a different number of workers. So we can see there is a lot of sensitivity to the number of parameter servers. The ideal number of parameter servers can vary based on the number of workers. But the other thing to take away, not only do we have to spend a lot of time tuning the number of parameter servers and changing it based on the number of workers, also your efficiency as you scale is really not very good. Even at just 64 workers, we're down to 20% parallel efficiency here. Which if your desire is to use a large portion of a supercomputer, you're not even close to that. So what this has led a few people to look at MPI-based data parallel TensorFlow and getting rid of the parameter server, taking that out of the equation and using MPI collectives instead of a parameter server to do this all reduce operation and averaging. So TensorFlow does have an MPI option, but all it's doing is essentially replacing the point-to-point gRPC operations with MPI. It's not getting rid of the parameter server, and it's not really using collectives. There are other frameworks beyond TensorFlow, such as Caffe and CNTK, that do a little bit better and include some MPI collectives within them. But the approach that we outline here, that Uber and that Uber's Horovod and Cray's plugin have taken, allows us to create how do I want to say this? A portable framework that can be plugged into different deep learning frameworks. So we can use the same code with TensorFlow, with PyTorch, etc. So just an outline of how this more scalable parameter server-free approach works. Here we don't have a parameter server. Instead, as we finish each of these steps of the process, we do a scalable global add, and then obviously a division by the number of ranks to get the average there. No parameter server processes. All of the resources of your machine are dedicated to gradient calculation. You're not dedicating any resources to just doing this averaging. So I mentioned already there's the Horovod framework from Uber. It's an open sourced add-on that they've currently added support for TensorFlow. PyTorch also works with Keras on TensorFlow. Essentially, you just need to replace the native optimizer with a new class that Horovod provides, and it uses an MPI all reduced between the gradient computations instead of the parameter server-based approach. Their latest version includes optimizations for nickel as well. It's available, open source, available on GitHub. Recently, some of the folks at NVIDIA have been contributing as well, so they have some interesting optimizations that they've applied for some of the GPU-based systems in addition to CPU-based systems. One nice thing here, no modifications to TensorFlow, PyTorch, Keras are required to use Horovod. You just need to make small changes to the user's training script. Similarly, the Cray programming environment machine learning plugin, sometimes we call it CPE ML Comm as an abbreviation, it works very similarly. In our plugin, we do not directly use MPI all reduce. We have our own custom written all reduce operation designed specifically for gradient aggregation and to run fast on the Cray Aries network. This was originally developed for TensorFlow and tested out with TensorFlow, but we were very easily able to port it also to PyTorch and to use it with crossover TensorFlow as well. It's also callable directly from C and C++ if you wanted to implement your deep learning in C++. Like Horovod, no modifications are required to the TensorFlow source, and we support also multiple gradient aggregations. We have thread teams that can be useful if you're doing things like generative adversarial networks where you may be training multiple networks at the same time. Another interesting thing in this approach, I won't get into the details really, but we support something which we call delayed synchronization. And there's been some interesting work recently that folks have done on the Summit machine with Horovod, where they've applied a similar technique that they call lag. The idea is the big problem with so asynchronous obviously gives you a benefit in that you don't have to wait at that synchronization point. The problem with asynchronous, as I mentioned earlier, is that your models can drift. But the insight here behind delayed synchronization, as we're calling it, or lag, as some of the folks who've been working on the Summit machine with Horovod have been calling it, the insight here is as long as you don't drift too much, you can actually keep your convergence properties fairly similar to what you get with pure synchronous stochastic gradient descent. So the idea there is basically you allow your gradients to be updated from the previous step. So you delay that synchronization by a step. So you compute your next step possibly with gradients, or possibly with a model that's just slightly out of sync. But it turns out in practice that doesn't matter very much, and you're still able to get good convergence, and you're able to get a lot better parallel efficiency by applying this delayed synchronization or lag approach. So here's a few numbers here from doing some tests comparing our plugin with both Horovod and with gRPC. Of course, I put the ones where the Cray version wins. I will say that there are other benchmarks. There have been some papers published at the Cray user group and other places that show that it can vary depending on what benchmark or what model you're running. So our actual recommendation is, we don't necessarily say that we're always better than Horovod. Try them both, and we'll help you work with both. We'll help you work with our plugin on the models where that works best. We'll help you work with Horovod where that works best. One of the things we've especially seen is that on some of the dense GPU-based systems, Horovod has a small advantage over our plugin. And on Aries-based systems, since we've put in some special optimizations there, our plugin tends to do a little bit better than Horovod. Not hard and fast rules, but that's kind of what we've tended to see in general. So as I mentioned, as you're scaling up deep learning, getting performance is one thing, but ultimately your goal when you are doing machine learning, when you're training the model, is you want the fastest time to accuracy. Your ultimate goal here isn't getting the highest FOP rate or processing the most images per second. Your ultimate goal is to get your model trained as quickly as possible. And so you need to think about some of the issues around convergence when you're scaling up. Because when you increase the number of workers that you apply to the problem, you necessarily have to increase your global batch size in order to actually keep those workers utilized. So if you're so the global batch size is basically, I mentioned we have our mini batch. That's what you process during each step, and we divide that amongst all of the processes. So if you increase the number of workers, you imagine if you want to actually keep all of your ranks utilized, all of your nodes utilized, you can't really shrink that local mini batch size down too small, so you're going to end up increasing the global mini batch size, which increases the number of images, number of samples that are processed in any given step, which means you may require more iterations to converge, and you may also lose some of the stochasticity of stochastic gradient descent. So stochastic gradient descent, because it looks at sort of small portions of your training samples at a given time, as opposed to looking at everything at once, it kind of does a bit of a random walk through the space because it's not looking at everything at once and saying, okay, this is all of my input. The best direction to move is this way. It's looking at a small piece, and so it may go off in slightly different directions, which helps it better explore the error space. As you start having your mini batch, your global batch size larger and larger, you lose some of that randomness and some of that exploratory capability as well. We see with these larger batch sizes, we often see cases of the model overfitting. So you may end up with poor generalizability, in that you may train really well on your training data, but when you then check it with your validation data, you see that actually the error is much higher there because you've overfit your training data. We see cases where the optimization is attracted to saddle points, and as I mentioned earlier, you're losing some of those exploratory properties that you can see with smaller batch size. So some of the steps that we take when we're first getting started with this, typically, one of the big things we want to play with is the learning rate. This turns out to be one of the biggest things that you can use to help you with this. So we usually start with whatever the recommended learning rate is for your optimizer of choice. And then you apply a multiplicative factor to that based on the number of parallel processes. So you could do it linearly, or you could do a square root approach. Different cases, they have different advantages. I actually talk about that a little bit more on the next slide. And then generally what you want to do is decay your learning rate during training. So as you go through your steps, you use a lower and lower learning rate. Run through all of this, look at the training accuracy, the validation accuracy, and then you can start playing and applying some of the other techniques that I will mention in just a second here. But first, just a quick note on square root versus linear scaling. So linear scaling can have an advantage here because you're moving faster through the space. If it works, it will often get you to convergence in fewer iterations. But we found that in many cases, it won't converge as well. So using a square root based approach is actually, I think, more mathematically correct. Some other observations we had, other things that we've found can help when we're trying to scale these up, is that we've seen often that using these linearly scaled learning rates, as I mentioned, cause the most problems early on in training. So sometimes what we'll do is we'll add sort of a warm-up set of iterations to reduce those errors. So during the warm-up, you might have a lower learning rate, and then once you're started down a reasonable direction, then you can transition back to the larger learning rate predicted by the linear scaling rule as opposed to the square root scaling rule. Also, at larger scales, using the momentum term can be very useful. So momentum term essentially modifies the gradient slightly by the previous gradient. So you think, if you're going through the error space in this direction, you turn there, you have a little bit of momentum. We've seen that can really help at large scale. Layer-wise adaptive rate scaling. So what this does is allows you to use different learning rates at each layer of your network. That can be very useful as well. And we've seen, especially with the delayed synchronization or the lag style optimizations I mentioned earlier, using a cyclic learning rate can be very effective. So here you may start, you may do a warm-up period and then go to a higher learning rate, decay that learning rate, then cycle back up to a high learning rate again, decay again, up and down, sort of in a cyclical pattern. We've seen many cases where that seems to help you get convergence faster. So these are just some of the tips and tricks I've seen. There's some great references that we've used as we've looked at all this, and these, I believe these slides are all going to be posted on the workshop website, so you should have access to all these links. But if you're really curious about some of these convergence properties of deep learning training at large scale, I definitely recommend these papers here. So the last thing I wanted to do was just point you to an example if you wanted to try out our plugin. As I mentioned earlier, both Horovod and the Cray plugin do require some small modifications to the training script you would use for non-distributed TensorFlow training. So both of them have fairly similar content of what you have to do to change them. Essentially, you need to import the Python module, of course, that you're using. Initialize that module. If you're training something like a GAN and you want multiple thread teams, you need to specify that. You need to broadcast your initial model parameters. You need to incorporate this gradient aggregation between the computation and model updates. So your typical training script would have the gradient computation and update as sort of a single step. Here we break that up and we add between the local computation and the update of the weights in the model, we add a step that does this all reduce, basically a call into either Horovod or the Cray plugin. And then you do a finalization that cleans up all of the MPI data structures and everything. So the example I mentioned, we've taken the MNIST training script from the TensorFlow, sort of official TensorFlow example, and we have modified it to use the Cray plugin. You can find it. My colleague Christy has set up the latest version of the Cray plugin 1.1.2 for Python 3 within her directory. So if you do this module load here, that will bring all of that in. This needs to be updated. Actually, I just learned a few minutes ago. This has changed. It's now, instead of module load TensorFlow, you need to do module load data science / TensorFlow / version. And I think this was designed, the examples we have here were built with 1.10. So you would do module load data science / TensorFlow / 1.1.0. And then you can look at our modified training script, Emacs, VI, less, whatever your editor of choice is, at that location. And if you want to actually try it and run it, you can, once again, load the module for the 1.1.2 version of the plugin. Here I did update I updated the TensorFlow module load there, so data science / TensorFlow - 1.10. And then you can do a simple app run, if you wanted to run it on 4 nodes. Enable the plugin here. This can be where you want your model training to occur. You can just do it in your home directory if you want. This points to the example script that I mentioned earlier, and that will run it. I just tried this example right before I came up here, so as of now, it's working. Wanted to make sure. So that's what I have. So happy to take any questions. Yeah, sure. Actually, that's a great question. So Venkat was asking about the adoption of model parallelism, and this is something that we've seen some people ask and inquire about, but we haven't yet seen any solid examples that really require model parallelism. But we are very interested. So if any of you have a great model that you think could benefit from model parallelism, we actually have been having some discussions internally about ways we could extend some of the techniques we're using in the plugin to support a hybrid model parallel, data parallel approach. And one of our roadblocks is that we don't yet have the good examples to kind of use to sort of optimize and test those ideas out. So if anyone in the room has some good examples, I'd love you if you came talk to me. Yeah, so the question was, why do you want to synchronize the models, and why can't you just combine predictions later? So more of an ensemble type approach. And that's actually an alternate approach towards training these models. You let everybody go off, you do basically independently train, and you know, there's various ways to combine the ensemble. In a number of models, we've found that this more synchronized approach works better, but not every model. There's certainly applications of ensemble-based training that we have seen. So I think it's more of a question of not one's better than the other, but which techniques works best for your particular problem.